Hey, chemistry people, it is Mr. Boylan. Are you ready for some more chemistry? Today, we are going to use thermochemical equations to calculate energy changes that occur in chemical reactions and classify those reactions as either exothermic or endothermic. As always, let's break that down a little bit. We're going to write thermochemical equations and sort of talk about what those are and how they differ from your other types of chemical equations. We're going to define and calculate enthalpy change for a reaction, abbreviated delta H, and use enthalpy change to determine whether a reaction is endothermic or exothermic. And then lastly, we're going to perform some stoichiometry calculations involving those thermochemical equations. All right, so if we take a quick moment to think about what the heck a thermochemical equation is, it's a chemical equation that includes some thermo. Basically, it's that balanced chemical equation that is include not only the physical states, but also the quantity of energy that's released or absorbed as heat in the equation itself. Now, as you think about sort of what that might look like and how that differs from your typical chemical equation, you're just going to see written in the equation itself an amount of energy, and that energy is going to be considered heat energy. You'll see it as either a product or a reactant. Now that heat of reaction, that's either one of your reactants, one of your product, is going to be known as enthalpy of reaction. And it's abbreviated delta H. It's just the amount of energy that's released or absorbed as heat during the chemical reaction. So new vocab word there. Make sure you commit that one to memory. But enthalpy is just a name given to your heat content of a system, your reaction, that occurs at constant pressure. Although we cannot measure the actual enthalpy of a substance, you can measure the change in enthalpy, or delta H, of your reaction, which is the heat absorbed or released in a chemical reaction. Again, this amount of heat energy absorbed or lost by a system, our reaction, is known as the enthalpy change, delta H. For the purposes of this course, the change in enthalpy, or delta H, is the same as Q. So we did some calculations in the last class with Q representing heat. For our purposes in this class, delta H will be equivalent to Q. Now, this enthalpy change, or amount of heat lost or gained, can be determined by the following formula. You're given this formula on your formula chart, but basically the enthalpy change for the reaction can be determined by summing together all of the change in enthalpy of formation for your products, and summing together all of the enthalpy changes of formation for your reactants, and then subtracting the enthalpies of formation of your reactants from the enthalpies of formation of your products. Now, that may sound a little tricky, but we're going to do a couple of quick examples here, and you'll find yourself humming through these problems without too much trouble, not a whole lot of struggle here. But before we do that, let's talk briefly about a couple of terms that we're going to hear a lot in this unit, and just important to sort of keep straight in your mind to better help understand what's going on with the flow of that thermal or heat energy. System, first of all, refers to a particular part of the universe that's being studied, and in chemistry, we're usually talking about our chemical reaction. So when we say system, we're talking about what's going on in our beaker, in our flask, the system that we're talking about. Surroundings, on the other hand, are everything that's outside of your chemical reaction. Universe, then, is the system and the surroundings combined. And when we talk about the flow of that heat energy, when we say a reaction is endothermic, energy is simply transferred from the surroundings into the system. Whereas in an exothermic reaction, that energy is transferred from the system to the surroundings. And again, if you sort of examine this little diagram that you're provided with in your notes, it's a pretty straightforward explanation of some of those terms that we just talked about. Just be familiar with them, recognize we're talking about system, we're talking about our chemical reaction, surroundings, everything else, universe is all of it combined. And then depending on what's going on with the flow of the heat energy, it's going to determine whether the reaction is endothermic or exothermic. Now, when we write thermochemical equations, it's important to note that oftentimes we write them by simply designating the sign of the enthalpy change rather than writing it as a reactant or a product. Okay, and as you take a look at a couple of examples here, you're going to have two equations, two in green, two in blue. The ones in green are thermochemical equations, but they have the heat, but they have the energy included in the equation as a reactant or product. You'll definitely see it that way, but more commonly you'll see those equations written as you see them here in blue, where the enthalpy change is simply written to the side of the reaction, and you're given a sign to let you know whether that heat energy is a reactant or a product. Is it endothermic or exothermic? And so just take note that when you've got those exothermic reactions, or where heat is given off or released as a product, your enthalpy change will be negative, and then your endothermic reactions will have that change in enthalpy to be a positive sign. So just to reinforce here, then, if you have an exothermic reaction, you're going to have a negative enthalpy change. And again, it's not that you have a negative amount of energy. The negative sign is just indicating the flow from the system to the surroundings. And this can be depicted in a couple of different ways. You definitely have your thermochemical equations, but you may also have to interpret a energy diagram that compares the energies of your reactants to your products. In this particular energy diagram that you see, you've got your reactants here, your products here. As the reaction proceeds, we find that our products exist at lower energy than our reactants do, and therefore our change in enthalpy will be negative. Conversely then, if you have a positive delta H, it indicates that you have an endothermic reaction, or that heat has gone into the system. And as you look at how that would differ in a energy diagram, as you take a quick look here, you've got your products now at a higher enthalpy or a higher energy than your reactants are, indicating a positive enthalpy change. Last couple things to think about here. We're going to talk about standard enthalpies of formation. These are pretty big, pretty important. It's the energy change when 1 mole of a substance is formed from its elements in their standard states. And you'll also see that represented as delta H sub F. Kind of an important thing we'll talk a lot about as we work through some of these problems. But again, standard enthalpies of formation, the key things here, it's 1 mole of a substance that's formed, and it's formed from its elements in their standard states. So we'll practice that, we'll take a look at that, but important term to sort of keep in mind. And then lastly, never going away, stoichiometry is coming back. You can expect to do stoichiometry calculations using thermochemical equations. Carefully examining your enthalpy change and comparing its coefficients. Just again, treat it as one of your reactants and products to continue doing some awesome stoichiometry.